To the rescue! Okay, here we go. A helicopter is flying to drop a supply bundle to a group of firefighters who are behind the fire lines. At the moment the helicopter crew makes the drop, the helicopter is hovering 400 feet above the ground. Okay. The time it makes the drop, the moment it makes it 400 feet above the ground. Okay. Makes the drop 400 feet above the ground. That's important. The principles of physics that describe the behavior of falling objects, oh yes, physics, state that when an object is falling freely, it goes faster and faster as it falls. In fact, these principles provide a specific formula describing the object's fall, which can be expressed this way. Oh, no way, they give you the formula. Y'all are lucky, usually they make you figure it out. If an object is dropped from a height of n feet, so that's our starting height, then the height as a function of time, the height in feet off the ground, t seconds after it's dropped, so that's in feet, I guess that's important, t is in seconds, is given by the equation h of t is equal to n minus 16t squared. Okay, in the case of the falling supplies, oh, and if y'all were in the Ferris wheel class, you made up this formula. So ask about people who are in heights if you need help for this. In the case of the falling supplies, the formula is h of t equals 400 minus 16t squared, because the supply bundle is 400 feet off the ground when it starts to fall. Okay, that makes sense, right? So 400 feet, that's the 400. Everything else stays the same because your 16 is your effect of gravity. One, what is h of 3? That is, what is the height of the supply bundle 3 seconds after it is dropped? Okay, well, let's answer that. H of 3, well, let me just write this down. So remember, our model, h of t is equal to 400 minus 16t squared. Then h of 3 is going to equal this same thing, but instead of the t, we'll replace it with a 3, right? Because it's 3 seconds. Oops, I wrote that wrong. Talking and writing is hard. 3 squared. So if we math this out, we know that h of 3 is going to equal, let's see, we'll do that later, 400 minus, let's see, we know we have to do, actually, if you don't know, this is a great tip to listen to, exponents happen before this multiplication. So we want to do 3 squared, which is 9, times 16. So it'll be 16 times 9. All right, I'm really committing to it. 400 minus, let's see, and then 16 times 9 is going to be 160 minus 16. Oh. 16 is 144. Double check and make sure that's right, because I just did it in my brain. And sometimes my brain's wrong. 400 minus 144 is going to be, let's see, that'll be 300 minus 44, which will be 256. And double check that as well. And so that'll be your 26 feet off of the ground. So after 3 seconds, that's how high the supply bundle is. Okay, how far has the supply bundle fallen during those 3 seconds? Well, let's think about that. If it started at 400 feet and now is at 256, what math did we do to get to that point? Well, didn't we just take this 400 and take away whatever this ended up being? Yeah, which was just the distance that it fell in t amount of seconds, which was 3. And if we did that math, we found out that it fell 144 feet, right? Because 144 feet, 400 minus 144 feet is where it's at right now. So it fell 144 feet. That's how far the supply bundle fell in those 3 seconds. What is the supply bundle's average speed during those 3 seconds? Hey, we can do that. Let's see. If we think about the average speed, We know at the point that it's dropped, let's see, so here it's like, here, this is its distance it's fallen. I'm gonna draw it going up, even though we know the supply bundle is falling, its distance from the point it fell is increasing. So just remember we're thinking about it kind of inverted. But we know at time 0, its height was 0. And then now at time of 3 seconds, its distance that it fell was 144 feet. So if we take the average of those, even though we know the speed wasn't constant, but we can take an average to model an average speed from that time that is constant. We can do our y2 minus y1 over x2 minus x1 to get our average distance per second. So that's going to be, let's see, we'll call this point 2, we'll call this one point 1, and this one's 0, 0. This one's 3, 144. So our y2 is 144 minus 0. Our x2 is 3 minus x1 is 0. And that's going to be 144 divided by 3. If I pull out my fancy calculator, where'd you go? There you are. We can do 144 divided by 3, which is 48. This is, of course, feet per second. 48 feet per second. Okay. How long does it take the supply bundle to reach the ground? Oh, that's interesting. I might have to use the back page for this. I'm going to use the back page for it. Okay, we know that our function is h of t is equal to 400 minus 16t squared. And we're wondering, what is its height, or what's the time when it reaches the ground? So, well, let's think about it. When it reaches the ground, what is the height going to be equal to? The height's going to be 0, right? It's going to be 0 feet off the ground once it's reached the ground. So I know we have this fancy function notation, which we usually don't touch. Let me refocus this. And we're just going to say, what if this height was actually equal to 0 feet? Then, if our height was 0 feet, then what would our time end up being? And we can actually, we could solve this. Another thing you could do is, of course, an in-out table and keep on, it's not going to be that much time until our thing hits the ground. So actually, why don't we do that? So let's see, our in is our seconds, our out is the height. So we know that at 0 seconds, our height is 400. We know at 3 seconds, the height is 256. Let's see, let's see where we're at 5 seconds. And so we're going to do h of 5, which will be 400 minus 16 times 5 squared. Oops, 16 times 5 squared. Oh my gosh, what luck. 0. I didn't know that. Okay, well, that's great news. So now we actually know that the answer is 5 seconds. That was Coach yawning, if y'all heard that. But I want to prove it. Let's go through this and let's solve this for t. So one thing we can do is we can take this term and add it to both sides. So if we add 16t squared to both sides, oops, add it, then a negative 16t squared and a positive 16t squared cancel each other out. So then we're left with 16t squared, right? Because 0 plus 16t squared is 16t squared, is equal to 400. Now we can divide both sides by 16, because we have to do the square last, because when we solve for t, we go in the reverse order of operations. Our 16s go away, and we get t squared is equal to, and this is 25, because 4 times 25 is 100. 4 times 4 is times 25 is 400. And then we have to do the inverse operation of squared, which is this, oh my gosh, that was a really bad drawing of it, which is a square root. And you'll find it on your calculator. It might look something like this on the iPhone, where it's the x square root of y, and then you can click that button. I think typically you'll have to type in this number first to do that. But what this does is this square root cancels out the square, so we're just left with t is equal to the square root of 25, which you can use that on your calculator to find, or if you know that 5 times itself twice is equal to 25, the square root of 25 is equal to 5. Okay, and is that our last question? Thanks for watching.